Hi, I'm Yiting Yan from National Chiao Tung University. Today, we are going to introduce our work, Inverse Halftone Colorization, making halftone prints color photos. Halftone printing has been widely used in presenting photographs on printing matter. It looks like grayscale, but in fact, it only contains black and white color and uses dots with various sizes to simulate different grayscale of images. In this paper, we aim to turn black and white halftone print into color photo. Our method can support random colorization and exemplar-based colorization. Given a reference photo, we can generate corresponding colorization results. This task can be viewed as a joint problem of inverse halftone and colorization. Inverse halftone is to turn halftone prints into continuous tone photos. Colorization is to transform grayscale photos to color photos. Even there already exists quite some prior works on either inverse halftone or colorization. To the best of our knowledge, we are the first of its kind to discuss such joint problem. Although the inverse halftone colorization seems to be achievable by cascading the inverse halftone operation and the colorization operation in practice. However, when we directly take the result of inverse halftone as input for the colorization model, the resultant photo appears to contain uneven color and diffuse contour, thus becoming unrealistic. In order to tackle such a challenge, we propose a novel framework for the task of inverse halftone colorization. Without loss of generality, for realizing the inverse halftone colorization, we can first perform inverse halftone and then apply colorization. Or in the opposite order, first perform colorization and then apply inverse halftone. Even both orders of cascading inverse halftone and colorization seem to be imperfect. We discover that the results from these two orders of cascade actually have complementary properties. The upper one has vivid color but with ripples, and the lower one looks like oil painting but retains obvious borders. Such complementary properties motivate us to design a fusion network for fusing the results from two paths, which brings many advantages, such as detail enhancement, artifact removal, and color tone correction, and finally achieve better results of inverse halftone colorization. Here is an overview of our architecture. There are three components: Inverse Halftone Network (IHN), Colorization Network (G), and Fusion Network (F). As introduced in the previous slide, we have two different orders of cascading the inverse halftone and colorization module. We use a fusion network to combine the results of both orders and benefit from their complementary property. In addition to our novel architecture of fusing two paths, we also design several novel objective functions, including similarity loss, histogram loss, and feature-based mode-seeking loss. Let's introduce each module of our architecture. We start from the inverse halftone network, which we name it as IHN for simplicity. This IHN network aims to recover the continuous tone image from a given halftone image. We additionally take a random noise map ZH as input for helping synthesize the information loss between the halftone image and its corresponding ground truth continuous tone 1. We chain IHN independently until it converges. Then we freeze the IHN and connect it with the colorization network G. The output of IHN, its H-map, and a color latent vector, ZC, are now taken as the input to the colorization network. In the colorization network, we have three different training schemes: recovery scheme, reference scheme, and random scheme, since our method aims to support random colorization and simpler base colorization. The main difference of each scheme is the source of color lantern vector, LC. In the recovery scheme, we use an encoder to transform the corresponding ground truth color image into the color lantern. In the reference scheme, we obtain the color lantern from the color reference image, in which we are performing exemplar-based colorization. In the random scheme, we draw from standard Gaussian distribution to get the color lantern, in which we are performing random colorization. Finally, with both IHN and colorization network well pre-trained, we can now generate two results from the opposite order of cascading these two networks. And we build up the fusion network by multiple residual blocks, which is able to enhance the future interactions across two paths. With the help of the fusion network, we can integrate the images from both paths and benefit from their complementary property to get better results of inverse halftone colorization. Here we introduce our several novel objective functions proposed by us. The first one is similarity loss. We divide the image into many patches and compute similarity between each pair of image patches. In this way, we can build up a patch-wise self-similarity matrix for each image. The objective is to reduce the difference of patch-wise self-similarity matrix between generated result and corresponding ground truth image, which highly encourages better coherence on the appearance for pixels of the same semantic class. The second one is histogram loss. We use a pre-trained histogram estimator to predict histogram, since the operation of computing the color histogram of an image is typically non-differentiable. The objective is to particularly consider the statistical similarity between the colorization results and their corresponding color references in terms of the color histogram, which could encourage the consistency between color distributions. The last one is feature-based mode-seeking loss. Mode-seeking loss encourages minor change in the color lantern code to have a significant impact on the colorization results. In general, the distance of the generated result is used to compute between image pixels directly. However, we compute the distance between the grand matrix of image features instead. This could better enlarge the distance in terms of style and ensure the diversity of colorization results to prevent mode collapse. In addition to aforementioned objective functions, we also have other typical or widely used loss terms in our model training. Please refer to our paper for more details. Here shows our results of inverse halftone colorization. For exemplar-based colorization, it will produce similar color statistics as the reference image. For random colorization, the color is diverse and plausible. Here comes the comparison between our proposed method and other baselines of cascading our IHN with different colorization models. We observe that these baselines produce artifacts, scattered color blocks, uneven color and diffuse contour, and low diversity with grayish color. In comparison, our proposed method outperforms these baselines to produce both diverse and realistic results of inverse halftone colorization. Please visit our session to know more details and have a discussion with us. Many thanks for your attention.